I want to welcome you to another statistical learning class. Of course, on Monday we started beyond linearity. I think what I'm going to do today, I'm actually going to have a kind of recap on what we did on Monday, and I'm going to also walk you through the non-parametric means of seeking redress. Generally speaking, uh, we at times we normally look beyond a straight line relationship where we're trying to model relationship between response and predator. Now, of course, if you take a look at what we've been doing before, like I said, we normally have a linear combination of the predators and the regression parameters. And of course, well, looking beyond that, how am I going to know whether the relationship is no, is not expected to be a linear? Of course, I can sketch a scatter plot. Of the scatter plot is a diagrammatical plotting of the response against predator. Now, when you take a look at what I'm trying to show you right now, the second module, the third module, the second module is polynomial regression. And of course, the third module, you can see we have sign. You can see sign and that. So whenever you have situation like that, we have non-linear relationship. It means we're looking beyond linear. Now, I need you to pay attention. Like I said, I'm having a recap. We have a wage data. We actually want to identify um, the kind of model that we're going to use in capturing the trend, the relationship between wage and age. Now, if I want to study relationship between wage and age, and I want to look beyond linearity, why am I looking beyond linearity? Probably maybe I've, you know, um, constructed a scalar plot where I diagrammatical plot wage against age, and I realize there's a curvature. Okay, there's a curvature means it's not a straight line, and we actually want to. So if it is not a straight line, then it means in estimating the function, we have to look beyond linearity. Now, in looking beyond linearity, the approach to estimate the functional relationship can be divided into two. We have a parametric approach. We have a non-parametric approach. I'm going to say that again. Within a non-linear platform, right now we're no longer a linear platform. We're in a non-linear platform. In a non-linear platform, there exist two major approaches that can be used to estimate the function that will enable us to capture relationship between wage and age. The first one is parametric, and the second one is non-parametric. Now, I'll first walk you through the parametric one. I'm also going to walk you through the non-parametric one. Okay, but what do I mean by parametric, and what do I mean by non-parametric? So when I say parametric, I'm actually assuming, of course, that if I if I'm going to state the model right now, please pay attention. If I want to state the model, okay, maybe I have x, okay, equal f of x. Okay, let me just say f of x. Okay, f of x plus the error. This is the specification of the model. But you know what I want to estimate? I actually want to estimate this particular function, okay? Because now estimating that particular function, if I'm going to use the idea of a parametric, then I'm assuming that this function, okay, has a specific functional form. I'm going to say that again. Uh, Parametric procedure requires that, in estimating this particular function, okay, this function is assumed to follow a specific functional form. It could be normal, gamma, and so on like that. But in the non-parametric approach, okay, we do not assume any functional form. Does that make sense? Okay. Now, what I'm going to do now, I'm actually going to want to explain. I want to start from the parametric, and I need you to pay attention. Okay. I need you to pay attention. Now, this is exactly what I'm trying to say. By parametric, the function assumes a specific functional form. And when it is assumed a specific functional form, that functional form is actually going to be a function of parameters. Okay. And when I'm not assuming functional form, okay, then that is a non-parametric. And also I said, we don't assume a specific functional form, but we have to estimate, okay, the function, the entire function. And at the end of the day, we're going to figure out which one, closely match. Now, I want to start, and I need you to pay attention. Now, you know where I want to start where I want to have my review now? I want to start from a parametric model. And the first in the parametric model I want to visit is polynomial regression. Why polynomial regression? Because I'm looking beyond straight line. I've already constructed a scatter plot between wage and age, and I realize there's a curvature. Whenever there's a curvature, then we can fit polynomial regression. Now, the polynomial, if you look at the equation two is a polynomial regression of a degree d, which is a generalization of a polynomial of degree 1 is a linear relationship. The polynomial regression starts from polynomial of degree 2. Now, let me tell you this. Why is this parametric? It is parametric because I'm still going to rely on the assumptions of normality to estimate the parameters. Take a look at that. I'm still going to use this guy. I want to estimate the beta naught, the beta 1, the beta 2, and so on like that, depending on the degree of polynomial. Okay, this is more or less like I have x1 up to x, s2, s3, and so on like that. But you know what? The x1 is x, the x2 is s squared, the s3 is s cubed, and so on like that. I'm going to have that as a design matrix. I'm still using the underlying distribution here is normal. And that is what makes polynomial regression a that's what make a polynomial regression a parametric method. Now, let me tell you this. In fitting polynomial, even though the polynomial is going to do a great job, okay, in bringing out the trend, but the issue with the polynomial, okay, it could overfit. I'm going to say that again. When you apply higher degree of polynomial, okay, you're going to get to a point where probably at the edge of the data, there's possibility of using what I call erratic prediction of the wage. And I'm going to show you that. Take a look at this here now. This is what I'm talking about. Okay. This is what I'm talking about. Okay. You can see from day one between the dashed line and the solid line, they match all the way to age 60. But you started seeing variance after age 60. You see the variance after age 60, then it means prediction at this region is going to be nonsensical. I'm going to say that again. Using, I'm using the degree of polynomial of 4 degree. Okay. Now using a polynomial, higher degree polynomial, like a polynomial of 4 degree. And of course, you're actually going to see here, there's going to be an erratic behavior when you know, at the edge of the data. Take a look at that. Now, and that was why I wrote this. The comments. When age is greater than 60, the variance is large. When the variance is large, that will lead to overfitting. High variance will lead to overfitting. Okay? Now, which means we need to be able to identify a model that we model that region perfectly. Because the way we have now, what we're seeing now, polynomial, or if we fail, even though polynomial actually capture most of the curvature in the data set, but at the edge, there's an issue. Now, what can be done? Okay. Now, there's another parametric procedure, okay, which is going to be an intervention. The intervention now is what we call step functions. Step functions is another parametric intervention. What do we want to solve? We actually want to solve a problem of overfitting created by polynomial of degree 4 at the edge. And what do we do? In the step function, please pay attention. In the step function, the idea of the step function, because we have issue in one category in the region, now the step function is going to say, you know what? Why can't you break the predator into maybe into beans, into intervals? Okay, and that's what you're saying here. You're breaking them. Maybe, oh, I'm talking about age. Maybe I should consider age less than 33, put them in one category. Between 33 and 65 in another category, and more than 65 in another category. Okay, and after doing that, I'm actually going to apply, you know, but the issue is I'm going to apply a constant, function for each of these, the constant. Okay, now I'm going to show you now the model for the step function right now. The model for the step function is equation 3. Please pay attention. Do you see equation 3? That is a model for the step function. Okay, this is still parametric. Parametric in a way, if I want to estimate the parameter, the beta naught, the beta 1, and so on like that, associated with each category. But right now, the predator that was continuous before, age was continuous before. But what do? We try to create, split that into intervals. Can you see that? Okay, now what do we see when we now fit this? Oh my God, this is what we see. This, I don't know whether you've seen in the high school, there's something that we call piecewise function. Piecewise function. Okay, if you take a look at what I have right now for each interval, take a look at this guy. A constant function, okay, in each bin, constant function in each bin. What is the problem created here? Okay, even though this was able to minimize the variance, but the problem created here is there is what we call a sudden jump. There is discontinuity. Discontinuity. You can see these guys, are they connected? They are not connected. That's what we call discontinuity. There's a problem of discontinuity. So this has an issue with discontinuity, and this also have issue with smoothness. Okay, so, and let me also tell you, uh, you know, this is assuming, for a particular age bracket, it's assuming the same behavior. For instance, let me talk about less than 33 years of age. Less than 33 years of age. Maybe I'm referring to 15 to 32. Okay, then 15 to 22. is assuming the same wage for all of them, even if variation exists within a class, it's actually going to ignore intra-class variation, which means it's not being localized. That is the advantages of this particular, step function. Okay, it loses information within being, and of course, may not provide a smooth transition. There's no smooth transition because you can see a break in all of that. Okay, now I'm actually going to move right now. This is another problem. What is the next thing to do? Okay, now the next thing to do now is, can we actually have okay, now after plotting that, this is what we have. After applying, this one is just to explain, right here, it's just to explain, for C1, the B naught, for C2 is going to be B naught plus B1, B naught, the intercept plus the B1, and so on like that. But when we apply that to wage, this is what we have. Please, I need you to pay attention. We apply step function to capture relationship between wage and age. Initially, when we apply polynomial, that was issued after age 60. After age 60, there's a large variance that could lead to overfitting. Because of that, when we actually spotted, we saw weakness with the polynomial. From there, we now want to apply a step function. Now, in the step function, we actually split the continuous age, look at that, to less than 33, to between 33 and 65, and more than 65, into 3 categories. But there's something I actually want you to see. Something happen here. Okay. Now here, the true relationship, okay, for less than 33 years of age, supposed to be a straight line. Okay. But look at what it's suggesting. What is it suggesting? It's suggesting a what? A constant, function for that, which means with a step function, we also have issue at the edge. Now, the issue that we have at the edge here is at the lower part of the edge. But for the polynomial, the issue that we had then was at the what? Anything more than age 60. Now, what can we do to solve this? Now, what we can do to solve this is to think about fitting. Can we have a way to combine the idea with the step function with the polynomial? I'm going to say that again. In the polynomial, we fitted polynomial to the entire data set without splitting. Okay. And we saw what happened with the step function. We break the predator age into different category. We feed it. We have an issue at the edge. But can we have a way to combine the step function and the polynomial? Now, I'm going to show you what we are thinking about. Okay, I'm going to show you what we're thinking about. This is what we're thinking about. This is what we call a piecewise polynomial. Okay, piecewise polynomial. Okay, now in a piecewise polynomial, the other time when we split the age into different categories, we maintain a constant function, right? Horizontal constant function. But right now, because maintaining horizontal constant function in a situation where a trend exists in in the locality, okay, in each category, okay, using a constant function is not going to be okay. And that was why I was okay. Can we fit polynomial for a particular age bracket and fit polynomial for the other age bracket? Okay, look at this. With that, we're going to choose a threshold that we call not, where we're going to split the point at which we're going to split the entire data set into two. We call that C. We go, okay, when the age is less than a particular age, I fit this polynomial of degree 3. When it is greater or more than that age, I fit this particular polynomial. Do you know what we call this polynomial? We call it a piecewise polynomial. A piecewise polynomial is using the idea of the combination of a polynomial and a step function together. Okay, when we do that, okay, why do you think we're doing this? We're actually doing that because when you take a look at the step function, okay, we said there's actually going to be a kind of a sudden change where there's no smoothness. There could be discontinuity. Let's see what we have. After doing this for the piecewise polynomial, oh my God, I needed to pay attention to what we have right now. I'm using, initially, when I fitted the polynomial, I use a degree 4. Why do I use degree 4? Because degree 4 we have more curvature than degree 3. The more you go in the degree of polynomial, okay, the more it become more flexible. But there's going to be an issue when you increase the degree of polynomial. More flexibility is not good. More flexibility will lead to overfitness. Now, right now that we are now combining the combination of a step function and the polynomial that we call a piecewise polynomial, this is what we have. Now, here, the threshold, the C is 50. Okay. We can actually determine that using the data, using the cross validation to be able to know what will be the knot that will work. Now, but there's something I want you to see. Oh my God, there's something I wanted to see. It's going this way before, and there was a jump. We don't want that. We want a function that will be continuous. Does that make sense? So using a piecewise polynomial now, you can observe a jump. After that age 50, okay, even though I said too flexible, because at the cut point, it can jump anywhere. When something is too flexible, then it can jump anywhere. Okay. And that look unnatural. When something is too flexible, it's going to create issue with interpretation. And that's why we don't try as much as possible in modeling to strike a balance between flexibility and interpretation. When model is more flexible, it could be very hard to interpret. Now, you saw the issue that we have right now. And don't forget, we have fitted the same degree of polynomial for this one and the same degree of polynomial here. And you see different shape. Any question here before moving forward? How many modules have I reviewed now under the parametric? I've reviewed polynomial module, regression module. I've reviewed a step function. Right now we're in under piecewise polynomial. So the three of them, actually fall under parametric or regression. How do we solve the problem here? How do we make sure it is continuous? Okay. Now, I needed to pay attention now. The only way we can ensure that is go by way of spleens. Spleens. Okay. To ensure that it continues, we actually going to apply what I call spleens. Okay. Now, let me tell you this. We have different kind of spleens. Okay. But the one that is very common is cubic spleen. Cubic spleen. Cubic is a third degree of polynomial. Now, I said, in order to overcome the problem encountered in the plot that I just showed you before, okay, because the plot that I showed you before was too flexible, and that was why there was a jump. I'll be referring to this one. It's too flexible. That was why there was a jump. Okay. And that actually will lead us to consider what I call spleen. And I said, okay, for instance, in order to exclude the possibility of jump, we don't want jump, then we require the curve to be continuous. And that is why in mathematics, I know in algebra, you've heard about continuity of a function and differentiability of a function. We don't want a sudden change. We want something smooth all the way. We want something that will continue. Okay. And that is where calculus is going to come into play. Calculus. Okay. Now, I said, however, even with that, we can still obtain a curve that is not natural, even with a cubic. Now, take a look at this. There's something we achieve here with a spleen. What do we achieve with a spleen? We achieve continuity, right? You can say continuity. But they say, look at it, we don't want this particular picture. Do you see that? We don't want that. That is not natural. Okay? Now, because if that exists, okay, if that exists, we could also overfit. Does that make sense? We want something that will look more smooth. And you know what we're going to do? Then we consider a natural cubic spleen. This is not natural. Now, you know what natural cubic spleen is going to do? The natural cubic spleen will impose a condition at the boundary. You know, this occur at the boundary, right? That occur at the boundary. You know what condition is going to impose at the boundary? The condition is going to impose at the boundary is the second derivative is going to set the second derivative to 0. I'm going to say that again. It's going to impose a condition at the boundary for this to look natural. And what condition is that? It will set second derivative. When I say second derivative, okay, the second derivative, f prime prime, okay, is going to set that guy to be equal to 0. Okay, and you know what is going to happen? That will flatten the curve. It's going to flatten the curve. Okay. Now, if you take a look at what I said ideally, we would like something similar to what is seen above, but it has to be smoother. So what I'm going to say, even though there is no discontinuity, but this is not smooth. There's a difference between discontinuity and smoothness. Even discontinuity, discontinuity is experienced here. Let me show you. This is an example of discontinuity. Okay. Now, but here with a spleen, we achieve continuity, but it is not smooth at the boundary. We want something smooth. Therefore, to get something smooth, we need to be able to, impose a condition at the boundary. And the condition we impose at the boundary is to set the second derivative to 0. Okay. Now, when we set the second derivative to 0, I need you to pay attention now. And that was why I said here, that can be done by imposing continuity of both the first and the second derivative of f at the north, at the boundary. And that very approach is what we call spleen. And take it, oh my God, you're going to see something now. This is the spleen now. This is a cubic spleen. You can say it is a kind of smooth. So this is the cubic one. This is a linear one. Okay, this is a cubic one. This is a linear one. Okay, but we want to make it natural because the one we want is natural. Okay, for the natural spleen, I said one of the main drawbacks of the using spleen is that they can lead to high variance at the boundary range of s. In order to address this issue, we can add further constraint, and that very constraint we are adding is to set second derivative to 0. Now, if you now want to see what is the difference, okay, I'm going to show you something now. Now, I needed to pay attention to this. I want to make it, take a look at this. We fitted both cubic spline and natural cubic spline on the wage, to model relationship between wage and age. Please pay attention. Okay. The natural cubic spline is the one in red. The cubic spline is the one. The two spline, okay, avoid discontinuity. Okay. The two, but one is, even though the two are smooth, but one is more natural. The one that is more natural is the natural spleen. The natural spleen is where we impose the second derivative. We set second derivative to be 0. And I want you to pay attention when you take a look at this. They align, but when you look at the confidence interval, okay, you're actually going to see that the natural cubic spleen is very narrower. Do you see how do I know it's narrower? Look at this. Give me 1 second. How do I know it's narrower? Do you see the natural one? But look at the cubic one. The natural cubic spin has a lower, as a narrower interval. Okay, why the cubic spin has a wider interval? We prefer the natural, cubic spleen. Now, all of these fall under parametric. But let me tell you this. What is crucial in a spleen, whether cubic spleen or natural cubic spleen, is how do you decide on the number of the knots, the boundary? How do you decide on the boundary? And that was why I said here. Take a look at that. But how do we choose the number of knots? It's very, very crucial. Okay? And to choose the number of knots, we can use a cross validation. Okay? To be able to know which one is going to be more appropriate. Okay? Now, is there any question? I'm done with the parametric. The parametric procedure that I've discussed. I discussed polynomial regression. I discussed the idea of a step function. I discussed a piecewise polynomial. I discussed splines. There are two types of spleen. I discussed a cubic spleen and I discussed a natural cubic spleen. Is there any question on that before I move to non-parametric? Is there any question before I move to non-parametric approach? Any question before I move to non-parametric approach? Okay, I want to welcome you to non-parametric approach. Give me 1 second. Okay, in the non-parametric approach, the difference is just like we're now assuming any functional form, okay, for our f, okay. But here, what do we do? Okay, we actually, and that was why I said, we now look at a non-parametric approach where no assumption, okay, on the functional form of f is made. Okay, but what do we want to do here? Okay, we only want to estimate f via a smooth function. Okay, we want to estimate our f via a smooth function. Of course, you all know why we need a smooth function. In a smooth function, we want a function that is continuous, and not only that. Let me tell you this. What do we mean? Let me first explain to you. What do we mean by a smooth function? A function that varies gradually with no breaks, no sudden change, and no sharp corners. I'm going to say that again. A smooth function, okay, a smooth function is a function, okay, And that particular function there is no break. There's no any break. There is no sharp corner. Okay, but it varies gradually. There's no sudden change. That's what we mean by smooth function. Mathematically speaking, what do I mean by smooth function? A function that is continuously differentiated up to a certain number of times. Maybe first order, second order, higher order, and so on like that. That's what we mean. The idea of mathematics is very, very crucial here. Now you know what smooth function means. Okay, function that varies gradually. No breaks. When I say no breaks, no discontinuity. That's what we mean. Okay, and sharp corner. Now, and I said the notion underlying smoothing is that the value of f at a location s is obtained by considering the values of the observed response variable in a neighborhood of x. Here, we actually want to consider some data point that are very close very close, because we believe uh those particular data point we have a greater influence on the estimate given any value of predictor. So, and that's why we want to ask some question. How do we define a neighborhood? Okay, because we want to do that within a neighborhood. How do we predict response locally? And how is smoothness ensured? Those are the questions that we want to ask, because we're actually going to seek redress using some data that are in the neighborhood. The question is, how do we create a neighborhood? And how do we predict response locally? And how is the smoothness, ensured? Now I need you to pay attention. Now we have a common way. There's a particular smoothing that is common that is called Kernel smoothing. Okay, Kernel smoothing. Okay, now the Kernel smoother will predict the value of the response. Here, the response variable is wage. The value of the response for a given value of age. Okay, using a weighted average of the observed values of y, where on the nearby observations. Okay, nearby. That was why I was talking about the neighborhood. Okay, now let me tell you this. If we want to do that, when I say weighted average of observations that are nearby, this is what I mean. Do you see that? That's a weighted average, right? That's a weighted average. Then where is the W coming from? That very W weight is coming from the kernel. Okay, and if I want to, we have different kinds of kernel density function that we can use. We can use, uh, a Patnikov. There's a Patnikov kernel. There's uniform kernel. Okay, we also have exponential. We have a Gaussian kernel. In fact, I'm currently working on an article that would likely going to take me to Colombia in the summer. Actually trying to reparameterize, Gaussian kernel density. Okay, so but what I'm trying to say right now is we actually want to use a weighted average. Okay, the weight is going to come from a kernel density function, and the kernel function, we have a common kernel function. But before I'm going to talk about that, take a look at this. This is where I'm going to find the weight. The weight depends on the kernel K and the lambda bandwidth. What do we mean by bandwidth? The bandwidth is going to tell us the amount of data that is nearby. Okay, the amount of data. Okay, that is what I think specifically I'm actually going to say call a bandwidth. I'm actually going to say you know, I really want to know the amount of data in the neighborhood, the amount of data. When I say the amount of data, like I'm trying to refer to like probably the percentage of the data. Okay. So that is what we actually call the bandwidth. And of course, you can see getting the weight. Weight is a function of the bandwidth. And I said the function, one of the common function used, okay, a very good choice. Okay, I said a function K is what we call the kernel, and it has to integrate to one. Okay, and assign the weight to the neighborhood location. Let me tell you this. Those data points that will receive more weight are those ones that are near the variable you are interested in. The one that are far away, they will have a lower weight. Does that make sense? The one that are far away, we have what I call a lower weight. So the bandwidth lambda, the bandwidth lambda is very, very crucial to smoothness. This lambda here, the bandwidth, the choice, the selection of bandwidth is crucial. Okay. So, like I said, uh, the bandwidth determines how much of the neighboring data point influence the estimate. How much of the neighboring data point influence the estimate. I'm going to say that again. The bandwidth lambda tell us how much of the neighboring data point influence the estimate. How much of the neighborhood data point influence the estimate? Those ones that are very close, that are very near, okay, will receive larger weights. Those ones that are far away receive lower weight. More weight means more influence. Okay, this is the kernel, the one that that we call a Pachnikov kernel. Okay, like I said, we also have Gaussian and so on like that. Now, I want to talk about lambda now. Okay, I want to talk about lambda, which is the bandwidth. Okay, like I say, it determines how much of the neighboring data point, okay, influence the estimate of the response variable given the predator. Okay, now when lambda is small, it has an implication. When lambda is large, it has an implication. When you choose a medium value for that, it has an implication. But there's something I'm going to tell you. He said, how do you expect the prediction to change as lambda increases? Please pay attention. Okay. I said the beta curve becomes smoother if lambda increases. It becomes smoother. But let me tell you this. We don't want it to be more smooth. When it is more smooth, there's going to be an issue. And we don't also want it to be less smooth. Okay. Now, take a look at this. Less flexibility, more smoother. When it is more smoother, it will be less flexible. Okay. And if it is less flexible, what is going to happen? The variance will decrease and the bias will increase. Let me tell you in statistics. When variance decrease and bias increase, okay, there's going to be an issue. Issue of what? Interpretability. Because bias is the worst enemy of everyone in statistical community. I'm going to say that again. Not even in statistical community. In the research world in general, bias is the worst enemy. Okay? I just want to... Now, because of that, how do we choose lambda? Because the selection of lambda is very crucial. Like I said, how do we choose lambda? Now, and I want to test this. Take a look at this. Okay, we can use a cross validation. Okay, now depending on the kernel you are using. Now, right here, I'm using a Gaussian kernel. for Gaussian kernel, when lambda is 0.5, when lambda is 5, and when lambda is 10. You know what I've done? When lambda is 0.5, that is when I have a small value of lambda, don't forget the bandwidth lambda tell us, okay, how much the neighboring data influence the estimate. How much? So if I use lambda to be 0.5, okay, I have an observation here. When the lambda is very small, when lambda is very small, okay, we're actually going to have high variance, low bias. You know, the other time I told you, when lambda is very large, what happens? It becomes more smoother, okay? There's going to be high bias, low variance. When it is small, what happens? When it is small, is if you take a look at this guy now, when lambda is very small, when the bandwidth is very small, when you only consider 50%, this one is, you know, I told you, lambda represent how much, okay, the neighboring data influence the estimate of wage given, I mean, of a wage given the age. If you take a look at this, you can see some fluctuation, right? Look at the red. You see some fluctuation. So here, even though we actually have low bias, but there is high variance. Does that make sense? Low bias, high variance. When you have low bias and high variance, then there will be overfitting. It means the model captured the noise. It performed it performed very excellently on the training, but poorly on the test data. Is there any question on the bandwidth equal to 0.5? Now, when it is equal to 5, oh my God, when it is equal to 5, this balances between, there's a balance between flexibility and interpretability. There's a balance when it's equal to 5. So what we're looking for, we don't want it to be too flexible. We don't want it to be more flexible. If you take a look at this, there's an issue here. Now, the issue here, the lambda, when the lambda is 10, when the bandwidth is 10, okay, I told you the other time. So we have I, you know, if you look at this one and this one, the one that is the major issue, let me just quickly tell you. This is a page I'm actually going to stop. Now, this one, there's an issue here. There's also an issue here. Okay. Now, when lambda is 0.5, we have a low bias, high variance for this one. Statistician will be happy for low bias here, but there's an issue with the high variance. But here, okay, low variance, high bias. Do you see that? It's also an issue. So we need to strike a balance. But using the cross validation, we'll be able to figure it out. Okay, we'll be able to know what is the appropriate lambda that work. Now, what I'm going to start from on Friday, I'm going to start from local polynomials. Let me tell you this: local polynomials is a non-parametric alternative to piecewise regression in the parametric. Okay, you know, the piecewise regression fits polynomial at different category, okay, using a parametric procedure. But the local polynomial now is using a non-parametric procedure, okay. We want to fit polynomial locally, okay. So I'm going to explain that to you. So this is where I'm actually going to start on Friday. Now, before I go, I slow down this week, not giving out a new assignment because I wanted to have a recap on what you've done before. I actually waiting before posting the review for midterm too because I want to finish the material the material for Friday. When I'm done finishing the material for Friday, then I'm actually going to release the midterm too practice. But like I said, make sure you have a recap on what you've done before. Okay. This is where I'm actually going to stop. If you have not yet collected your exam one booklet, I have it here. Make sure you all stay safe. See you on Friday. Bye for now, everyone. So,